Another fun consequence of special relativity is this idea that mass and energy are not different things, that you can convert mass directly to energy, and that energy can be converted directly to mass through probably the most recognizable thing in math ever, E equals mc squared. Okay, now all this seems a little crazy, and you might be skeptical about it, except that there's a high probability that your house is powered by a nuclear fission reactor, and it is also, depending on where you live, likely that your parents work there. So the fact that this is true is powering your house right now, right? This idea. Also, human beings have built weapons, right? And like the nuclear explosive devices operate on this principle. So this isn't nonsense. It has been proven again and again and again to be true. So you're going to have to just take a minute to wrap your brain around it. Fortunately, the math we're doing in this unit is not terribly complicated. So it leaves you with some extra calories to roll around and not sleep at night instead. What are we doing? Right. Okay, so for example, suppose you went out and bought yourself a little packet of roasted almonds, and I found one this morning, and it was 50 grams of roasted almonds. Now I looked on the back of that thing, and I found that it had some food energy listed on the label, was 320 calories, which after some research I figured out was 1,400 joules of energy. So that means that if you put 50 grams of roasted almonds into your mouth and run them through the frightfully inefficient process that is your digestive system, you would end up extracting 1,400 joules of chemical energy from those almonds by breaking down the sugars, breaking down the proteins and the fats inside of it. You would be able to extract that much from chemistry. Well, that's pretty handy, because you do need that energy to live. But what this little equation up there is saying is that the almonds themselves are composed of matter, and that matter can be converted directly to energy if you knew how. So how much energy would that produce if we actually drop 50 grams into this particular equation? Well, so instead of a chemical digestive process, we're going to go with a full-on mass to energy digestion, which would be neat. So we're going to get some energy out of this. We're going to take the mass of those almonds, we're going to multiply it by the speed of light squared. So 50 grams in kilograms would be 0.05. C squared is 3 times 10 to the 8. And if I square that, I'm going to get my calculator somewhere else. Alright, 3 times 10 to the 8. Square that times 0.05 gives me 4.5 times 10 to the 15 joules, which is a little more than that. Okay, so maybe we should try and park some metric prefixes on here. That would be 4.5 times 10 to the 12 kilojoules. I borrowed 3 powers of 10 and put them as a prefix. Which would be 4.5 times 10 to the 9 megajoules. Okay, that's getting better. 4.5 times 10 to the 6 gigajoules. 4.5 times 10 to the 3 terajoules. And for those of you with hard drives, bytes, kilobytes, megabytes, gigabytes, terabytes, this is the biggest hard drives that you can buy right now. And if we were to go one more, finally consuming our powers of 10, I would get the next level up, which I think is a petajoule. PJs, that's fun. Okay, so 4.5 PJs contained in those roasted almonds, and your body's only able to extract 1,400 joules when there's really that much available. Now, what would this kind of digestion look like? Well, the almonds would go in, and then they would be destroyed. Not like ground up into dust, not like ground up into bitty bits that were so small that you couldn't see them, or a paste. They would literally cease to exist, and what would be released in their place would be heat and light, which you'd have to absorb somehow. Absorbing this much energy from an almond would be challenging. So obviously your body is not capable of doing direct mass to energy digestion, and because there's massive amounts of energy trapped up in things. If you think about these almonds, 50 grams of almonds go in and 50 grams of whatever comes out the other side. You haven't lost any energy, you haven't lost the mass, you've just converted it to a different chemical. And in the process of breaking the chemical bonds, that's where this energy comes out. Here, we're literally talking about undoing matter and rendering it directly as energy. Okay, so just for fun, this particular number here, 4.5 petajoules, if I get rid of all these metric prefix things, takes you about 24 hours to digest your food. So what if it takes you 24 hours? Okay. Good. So that's a time. 24 hours times 60 minutes times 60 seconds. That would give you 60 times 60 equals 86,400 seconds. Okay. Now if I have an energy that's released and I have a time it takes to do it, then I can calculate a power output. So the power output of your mass to energy digestion would be 4.5 petajoules divided by 86,400 seconds. Times 4.5 just into 15. 5.208 times 10 to the 10 watts. So that's 52.08 times 10 to the 9 watts. That's 52.08 kilomega gigawatts. All right. And just for scale, the Bruce Nuclear Power Plant, located in beautiful Kincardine, Ontario, happens to have a total output of 7.3 times 10 to the 9 watts. Okay, so this little setup here is 8 times larger than the Bruce Nuclear Facility's total power output. And keeping in mind that the Bruce Nuclear Facility is currently, as of today, the largest operating nuclear facility on planet Earth, dissolving 50 grams of roasted almonds over 24 hours, if you were doing pure mass to energy consumption, would be 8 times the power output of that facility. So if you think about that, if 50 grams over 24 hours is generating this kind of energy, which is 8 times that, then this power plant must be converting about 1/8 of this mass every day. 1/8 of that would be about 6 grams. So the nuclear power plant at the Bruce facility, is chewing up about 6 grams worth of matter and turning it directly into energy every day. Neat. That's not a lot of fuel. So I'm going to sort of leave you to ponder this. The problem sets have a few of these silly kind of calculations, right? Like it'll either give you a power and ask you how much a mass would have to be chewed up in order to produce it. It's basically just this question in different directions. So, why is this a thing? Okay, now for those of you who have lots of calculus, this will make lots of sense. For those of you who don't, there will be some hand waving here, certainly. I've written out a bunch of this in the notes down below, so you can take a read through those, but you do not need to understand them. First thing we're going to do here is we're going to write down a thing called the Maclaurin series expansion of the Lorenz factor. Okay, now Maclaurin series expansion is a thing you're going to do in your first or second year university. It's a little calculus trick where you approximate a complicated function with a polynomial. So you write this thing, which, if you recall, is a reasonably complicated looking function. And we're going to approximate it by something that looks like this. 1 plus, let me look it up so I make sure I get it right, v squared over 2c squared plus 3v to the power 4 over 8c to the power 4 15 v to the 6 over 48 c to the 6. Now this thing that's happening like magic before your eyes, I tried to explain briefly how to do it in the notes, and you can look it up online if you'd like some interesting enrichment work. I can't talk and write at the same time, so here I am. I'm almost done. Dot, dot, dot. Okay. So there's a calculus trick that lets you write a complicated function as an expansion of that function that has an infinite number of terms. And the more terms you put on there, the better it gets. So if you want to test this thing, and I strongly suggest you do, you should put this into Desmos, or something that can sketch for you. Put that in. And then put this term in alone, and see how well it approximates. And it does not very well. Put just these two terms in, and it will get better. These three, it will get better. And as you add terms, this gross polynomial starts to look exactly like the sketch of that graph. If you put this many in, then the approximation is good up until about 2.5 times 10 to the 8 meters per second. So that's getting pretty close to speed of light, generating right terms. Okay, so this thing up here is just a calculus trick if you apply it to gamma. So I'm going to pull a few other little tricks here. I'm going to take this whole thing and I'm going to multiply it by c squared. And you might be asking why I'm doing that. Well, you'll see in a minute. So c squared of gamma would be c squared times 1 would be c squared. C squared times this term, right, if I put it in there, would end up dividing out the c squared there, and I'd be left with v squared over 2. In this term, I'd end up with the 3 kicks around, the v to the 4 kicks around, and this becomes 8c squared. This would be 15 v to the 6, 48. Oh goodness, that should have been a 6 down there. So this would be c to the 4, etc. Okay. The next thing I'm going to do is multiply this whole line by m. Now m is going to be the proper mass of an object. So we did a little bit on the relative mass, or the faster you go, the heavier you appear to be. We're going to put in a big old capital M for your true mass. So that's if you are not moving at all. So that's a tricky thing to accomplish, right? Everything in the world is moving. The Earth spins, it also orbits the sun moves around the center of the galaxy is in motion somewhere else. So if you were to truly find a fixed point in space and sit there, then this is what your mass would look like. If I take this thing here and I multiply it by big M for my true mass, I would have my true mass multiplied by c squared multiplied by gamma, which is going to give me my true mass multiplied by c squared plus my true mass multiplied by this term plus my true mass 3m v to the 4 over 8 c squared dot 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 etc. Okay, so what are we doing here? Well, if you notice in this particular term, that right there is 1/2 mv squared. That is kinetic energy, your true kinetic energy. All right. So this is an energy. It's measured in joules. And if all of these things are added to it, like you can't add things that don't have matching units. So this can't be kilograms and this be joules, because you can't add those things. They have to match. So if this thing is kinetic energy measured in joules, then this is an energy. So is this. So is this. Okay, so great. These things are energies. What are the energies of? Well, this thing here, kinetic energy, let me write that down, kinetic energy. That's the amount of energy it takes you to go forwards or backwards or up or down or left or right. This is the energy it takes to move through space. Okay, great. But I want you to think a little abstractly here, and I want you to think about going from your house to the grocery store. Okay, so you can see yourself doing that, no problem. You have to move through space in order to do it, because well, I assuming you do not live at the grocery store, you have to move through space to do it. But the thing that maybe never occurred to you is that you also must move through time in order to pull that off. You can't leave your house at 9 in the morning and arrive at the grocery store at 9 in the morning. You have to have arrived at a later coordinate on your time axis. And I think on a board up here we had something that said that space-time was curved, right? Space-time, this idea that you can't just move in X, Y, and Z, that in order for you to move, you have to move in x, y, z, and time. So your motions are all four-dimensional. If it takes energy to move this way, and it takes energy to move this way, and it takes energy to move this way, then it logically should require some energy to travel through time. And I don't mean that in a like poof, I'm in 1965 kind of time travel. I mean like literally just existing and flowing with the entire universe as time goes by. So that's what this thing is. Ish. Energy to flow through time. Which would give you your total relativistic energy. Okay, so the amount of energy that's required for an object to exist in four dimensions is these terms. They have one here that is independent of how quickly they're traveling through space, because it is how much energy is required to go through time, an energy amount that is required to move them through space, and then a whole bunch of other terms back here that mean probably something important, but certainly I don't know what they are. So if you and a rock, or better, you and a bag of almonds are in a train together, traveling with some kinetic energy, that's fine. You're all traveling at a certain speed. But you're also traveling together through time, right? Like seconds are ticking by for both you and the almonds. And if you were to suddenly extract that energy from the almonds, well, they can't do this anymore. So that matter doesn't travel through time anymore. It ceases to exist as matter, and it becomes its pure energy equivalent. So this mc squared here is possessed by every chunk of matter simply because all matter passes through time together. And if you can find a way to stop some piece of matter from traveling through time with you so that it transmutes directly to energy, then you can extract that either through a thermonuclear explosion or through a controlled reaction inside of a fission reactor, or inside of a not so controlled but really sort of inevitable fusion reaction at the center of a giant like a giant ball of matter, like a star that's collapsing. Whew. Neat. Did you understand this? Probably not, and you don't have to. It's not important. Did you understand this? I hope it makes a little bit of sense. It doesn't make a lot of sense, actually, and that's okay. You just sort of have to wrap your brain around it, and after a good long while thinking about it, you'll just accept it, whether it makes sense or not. There's way more math involved in trying to do this. The idea of crossing through a space-time interval, I tried to convince you of that down in the notes, so you can take a read through that if you'd like. Otherwise, it's off to the problem sets where you're basically plugging in numbers for two of these things and solving for the third. It's very, very grade 9. So don't panic. Take a look at the problems, and good luck.